Okay, so this is chapter 13 and this is the second lecture about this topic, not these little short lectures that I'm recording. And now we are going to talk about expansion. We already said that most materials expand when they are heated up. And now let's try to make this more formal. Let's try to write some equations. No? So here you have the sentence, most substances expand when heated and contract when cooled. But the amount of expansion or contraction depends on the material. Very well. So let's assume that I'm dealing with an object that is almost in one dimension. Okay, so it's almost like a wire. And yeah, I heat it up and I'll say that the length will change and I'm going to write delta L, the amount that changed, the amount that this material expanded. Okay, now what is this delta L? What does it depend on? It depends on the material, as we read. No? So we said that the expansion and contraction depends on the material. So it depends on the material. I'm going to write this dependence with this symbol alpha, which is the coefficient of linear expansion. The value of alpha will depend on the material that we're dealing with. Okay, what else does this delta L depend on? It depends on the initial length of this material, no? This object that I'm studying, and it depends on the change in temperature. Okay, so this is delta L. Let's think a little bit about units. Well, this change in the length will be given in meters. This original initial length is also meters. The temperature, the change in temperature, we'll be using Celsius, okay? Celsius, and this alpha, which is the coefficient of linear expansion, will be Celsius minus 1. All right, now we are going to solve some problems. I'm going to read it first with you, and then I'll let you stop. I think my suggestion is you stop the video, try to solve, and then we come back and solve together. But let's see. So this is the change, no, by how much this material will expand if I'm heating it up, or by how much it will contract if I'm cooling it down. And if I want to know then what is going to be the final length of this object, then the final length L will be the initial plus this delta L. This delta L may be positive or negative. No? Positive if it's expanding, negative if it's contracting. And given what this delta L is, if I put it here, I can write this equation as L equals to L0 plus alpha L0 delta T, T here for temperature, and then I can put this expression in the same form that you see here in this slide. L is equal to L0, 1 plus alpha delta T. But well, the important thing is to know by how much we will change, no? What is the delta L, and then if you need, you can compute the final length. Okay, so now we're going to read the problem. I suggest that you stop after reading it, try to solve on your own, and then come back to see if you arrived at the right answer and if you solved the problem correctly. So what is the problem telling us? Well, we have this steel bed of a suspension bridge. Remember that I said that a bridge is a special case on the road. No? It may expand or contract more than the road itself. And this bridge is 200 meters. Okay, so I'm going to write this L0, this L0 being 200 meters because this is the original length. And this is the length when the temperature, I'm going to call this the initial temperature, is 20 Celsius. All right. If the extremes of temperature to which it might be exposed are, so there are two possible final temperatures that this bridge can be subjected to. When it's very, very cold, it can reach minus 30 degrees. When it's very, very hot, it can reach 40, plus 40 degrees. Okay? And we want to know how much will it contract? So what is the delta L when this is the final temperature? And how much it will expand? So what is the delta L when this 40 degrees is the final temperature? What else do we need? Well, they told us what the material is. So we need to go to a table to see what are the values for the coefficient of linear expansion, the alpha, for the different materials. In this problem, they give us what it is. No? So they say the alpha for steel is 12, 10 to minus 6 centigrades, Celsius minus 1, because we the temperature, as I said, will be given in Celsius. Okay, so you know how to solve this problem, right? Stop, try to solve, and then come back to check. But what is the idea? Well, to find the delta L, we have the expression. So let's put here the delta L for contraction. What are we going to put here? We are going to use the alpha, this value here. So we have the alpha, I just put it here. L0, L0 is 200, so I'll put it here. Final temperature is minus 30. What is the initial? 20, so minus 20. So from here you're going to get a number. It will be negative, of course, because we are talking about contraction, but they just ask how much we contract, how much we expand, so you can just say the final value. And so it looks like the answer here should be 0.12 meters, which means 12 centimeters, as you see in the answer. And how about expansion? It's the same story. We just have to substitute, plug the numbers into the equation. This delta L will be that alpha 200. Now the final is that high temperature 40 minus 20. So this number here will be 20. And this will give us a positive number because we're talking about expansion, and it looks like it will be 0.048 meters, which is that 4.8 centimeters shown here. Very well, let's then continue. We have now another problem to solve. Let's erase this one, and let's read what is this other problem. So now we have an iron ring. Okay, let me erase and then we'll read together. Okay, so what is this next problem? We have an iron ring is to fit snugly on a cylinder iron rod. Okay, so let's try to understand first what they are telling us here. We have this rod, this cylinder here, okay, and we have a ring. So I have my ring here, and I want the ring to fit. I want to put this ring around this cylinder. Okay, so you understand the idea, right? Okay, now the problem is that at 20, so down they are going to give us the values. Né? At 20 Celsius, the diameter of the rod, so this value here, this diameter of the rod is 6.445 centimeters. Okay, while the inside diameter of the ring, so this part here, this diameter here, is 6.420 centimeters. So there is no way I can put this ring around the cylinder. The diameter of my ring, so the diameter of this ring here is much smaller than the cylinder. But let's read. Let's continue. This is the case when the temperature is 20 Celsius. So then we can play maybe with this idea of expansion, and this really is what people do in industries and when they are building devices. What is the idea here? They say, well, to slip over the rod, the ring must be slightly larger, and it must be larger, must be slightly larger than the rod by this much. So what do we need? We need that the diameter for the ring be the diameter for the rod plus 0.008 centimeters. So if this is satisfied, we'll be able to put this ring around the rod smoothly, easily. Okay, well, how can I do that? How can I expand? How can I make sure the diameter of the ring becomes larger than what it is originally? Well, what I have to do, I have to heat it up. No? So this is really what people do in companies. What engineers do and technicians working to construct different objects, pieces of cars, for example. Okay, so the question is now, what temperature must the ring be brought if its hole is to be large enough so it will slip over the rod? All right, so this, we know what we need. No? We know what is the final L that we need. So the final L is this number that you can compute, 6.445 centimeters plus 0.008 centimeters. This is what we want. So this is the final L for the ring, the diameter of the ring that we want. What is the initial diameter for the ring? What is it that we have at the moment? This one in red, no, the 6.420 centimeters. Okay, what I'm going to do, I'm going to put everything in our equation. No? So these two pieces of information I'm going to put in our equation. This is what we have at temperature 20 Celsius. To have this new value, that's what we have to find out. What should be this final temperature? So 20 is our initial. What should be the final temperature? Okay, so what is the equation that we need to deal with? The one that gives us the total final length. And that is L equals to initial 1 plus alpha delta T. Okay, final is this L of the ring here. So this is what we have to put in the place of L. Initial is this initial one here. Alpha, well, we are talking about iron, and the problem gives us what this alpha is. So I have to substitute this value 12, 10 to minus 6, right? And now for the temperatures, what should I put? Well, the final one is what I don't have that I want to find, and the initial is 20. Okay, so that's it. So now what you need to do is to solve this equation to find this final temperature. And if you do it correctly, you should get that this final temperature is really high, 450 Celsius. The next slide is still about expansion, but not for one-dimensional objects, but now we are thinking about volume. So we have what we have in mind now is expansions of three-dimensional objects, also of liquids, like in a tank, as the problem that we are going to solve. So what is the equation that we are going to use here? Very similar. It's very similar to what we had so far, but instead of length, instead of L, we are going to be talking about volume. We'll be talking about V. Remember that for the change in the length, we said that this was delta L, that depended on the material, depended on the initial length, and depended on the change in temperature. Well, now we are talking about volume, so the change in the volume will depend on the material. I'll put this letter beta now. Will depend on the initial volume and on the change in temperature. So it's pretty much the same thing, but instead of putting alpha, we are now using beta. Beta is the coefficient of volume expansion. It's the coefficient for this expansion that depends on the material that we are dealing with. Since we are dealing with objects that are 3D, it's close, but it's not exactly the same, but it's close to 3 alpha. Okay, So that's the same idea as we had before, but instead of length we are putting volume, and you have to be careful with which constant you're going to use there, which coefficient you're going to use there. Let's then solve a problem. Again, my suggestion is I can read the problem with you. After I finish reading, stop, try to solve, and then check if you solved correctly. So what is the problem? And this is a real issue. It's something to think about. What we have is a steel gas tank. So it's a tank, gas tank made of steel. The volume is, the initial volume is 70 liters. So this is the gas tank of a car. And suppose it's filled to the top with gasoline at 20 Celsius. So this is something that you should never do. Now, when you go and fill your tank, the tank of your car, never fill it up all the way to the brim, all the way to the edge. Now, when you're putting the gas, you know that the machine stops by itself. Now, when it detects that it's already getting very much filled. And why? Because if it gets hot, if there is expansion, the gasoline may overflow, and this is very dangerous. Okay, and this is exactly what this problem is about. Okay, so someone filled his tank all the way to the top with gasoline, and the car is initially at 20 Celsius, and let's see what is going to happen. So this is a very dangerous scenario. Look at this, what the problem says, that the car sits in the sun, and the tank there in the sun, so this was the initial temperature 20, but then the tank now reaches 40 Celsius. The tank now reaches 40 Celsius, and we want to know how much gasoline should overflow from the tank. And why should it overflow? Because the gasoline will expand, this liquid will expand more than the tank that is made of steel. How do I know that? Look at the coefficient of volume expansion, which is given to us. The coefficient for gasoline is 950 10 to minus 6. Much larger than what we have for steel. For steel, oops, sorry, I used the wrong letter. Let me, not alpha here. Now we are talking about volume, so it's beta. For steel, it's much less. It's 35 10 to minus 6. Okay, so we know that the gasoline will expand much more, and since it's already at the border, since it's already at the top of the tank, will then overflow. So that's the very dangerous scenario that I'm telling you about. Okay, now by how much will the gasoline overflow? Well, let's see by how much the tank will expand and by how much the gasoline will expand. So we can go back to our equation, which is also written in our slide. So you have the delta V is equal to beta, the initial volume, and delta T. Okay, we'll find the delta V for gasoline, so you can find it. Let's just detect what are the values that you're going to put. Beta for the gasoline, so you put it there. Initial volume, well, the initial volume for both, for the tank and for gasoline, is 70, right? So beta for gasoline. Here you're going to put 70 liters. And delta T, well, final is 40 minus 20, so this change is 20 Celsius. So here you're going to get a value. And do the same for the tank. So beta is for steel, 70 is the original, and the change in temperature 20. Okay, so then if you put there, you will see that the gasoline, the value that you will get from here is the gasoline expands 1.3 liters. Okay, and the tank increases up by almost nothing, 0.05 liters. So that's almost nothing in comparison. So you see that more than 1 liter will overflow. So that is the scenario that I said is very dangerous.